This conference will now be recorded. This conference will now be recorded.
Hello students, very good evening. Today we are continuing with the Ray Optics chapter. So today's topic will be refraction of light and related various natural phenomena. Okay, so the topic we are going to discuss today is the total internal reflection, refractive index, and relative refractive index, the relation between speed of light and refractive index, etc. And in the total internal reflection part, we'll see how mirage is formed in the nature due to total internal reflection. Okay, so let us start our discussions. So first we will be discussing the what is called refraction. Okay, see, when a light is incident at the interface of two media, like say there is some medium, air, and this is water. Okay, so this is the interface between these two media, which is separating these two media. And if light just falls obliquely at this interface, then what we see is, see, the part of light, incident light, will be reflected back to the same medium. Okay, that to the air medium, like this. And the other part will be actually refracted. Okay, refracted, as you see here. Part of light will actually enters into the other medium. Okay, part of the light, incident light, will be reflected back. Okay, and the other part or the remaining part will be entering into the second medium. So this is the ray which is entering into the medium, second medium. This ray is called refracted ray, and this phenomenon, like while entering into the other medium, the ray is actually getting bent. Okay, getting bent, or it is deviated from its original path. Okay, or path of incidence. So this phenomenon of bending of light at the interface of two media is actually called refraction of light, and the ray is called refracted ray. And you know, as we have discussed earlier, that the incident ray or incidence, angle of incidence or angle of reflection or angle of refraction, they are always measured with respect to the normal drawn at the point of incidence. Okay, and it is normal to the interface here. So the ray which is entering into the other medium is called refracted ray. So here I have written the phenomenon of change in the path of light as it passes obliquely from one transparent medium to the other medium is called the refraction of light. Okay, that is called refraction of light. And see, we'll learn once again the laws of refraction. You might have been learned, like you might have been learning this reflection of light since your 9th standard and all. Okay, so what are the laws of refraction? Laws of refraction. First law of refraction is saying that the incident ray, refracted ray, and the normal to the interface at the point of incidence all will lie in the same plane. Okay, that means this one. Okay, this is the normal to the interface, This is angle of incidence, sorry, ray, incident ray. This is reflected ray, and this is refracted ray. I'm talking about refraction, so I can just draw like this. Okay, so this is the angle of refraction, this is angle of incidence. So the incident ray, refracted ray, and the normal to the surface interface will all lie in the same plane. So this is first law. Second law is saying that the ratio of the angle of sine, the ratio of sine of the angle of incidence to the sine of angle of refraction is constant for a given pair of media. I'll explain what it is. See, sine I, suppose there are two media, okay, media 1, this is media 2, and a ray of light is refracted from medium 1 to medium 2. Okay, it is getting refracted from medium 1 to medium 2. So this is angle of incidence, this is angle of refraction, and suppose refractive index, I'll just come to that point. So see the angle of sine of angle of incidence I, and if you take the ratio of the sine of angle of incidence to the sine of angle of refraction, then it is going to be a constant. Okay, but this constant is not an arbitrary constant. Okay, this constant depends on the pair of media. Okay, this constant depends on the pair of media. And you know, you'll be surprised to know, according to Snell, this refractive index is actually called relative refractive index. Relative refractive index of the medium 2 of the medium okay, medium 2 with respect to medium 1. Okay, I'll just explain what it is. See, this constant, suppose the refractive index of the medium 1 is mu1, and the refractive index of the medium 2 is mu2. You just now, for the time being, you just hear the word or just learn the word refractive index. I'll explain and I'll define what is refractive index as we go along. Okay, so this is okay. So according to Snell, actually, say mu1 sine I. Okay, refractive index of the medium 1, where the light is incident. Okay, light incidence at this medium, right, in the first medium, and it is equal to the refractive index of the medium 2 and the angle multiplied by the angle of refraction. Okay, so this law is actually called Snell's law. This is called Snell's law. French scientist has discovered this law, okay, or this relation. And you know, then what is this constant? Now, can you tell me what is this constant? This is not an arbitrary constant, as you see. It is actually, this constant depends on the medium, okay, or the pair of media. Okay, that's why this constant is see, if this is air I'll write later, and this is water. I'll write what this value is. See, sin I by sin r means mu2 by mu1. Okay, that means refractive index of the medium 2 to the divided by refractive index of the medium 1, and this could be written as this mu2 1. Okay, and this constant, see, this constant depends on only the medium 1 and medium 2. If suppose I take an example of air has got refractive index 1, okay, and water has got refractive index 1.33, okay, 1.33. So in this case, what will be this constant? This constant for this is happening at air, right? Air sin r, this is actually in water. So in this case, write the refractive index of the second medium and then the refractive index of the first medium. So this constant is 1.33 for this pair of medium, like pair of media, air and water. Okay, so this is not an arbitrary constant, and you hopefully you have now can remember the Snell's law that you have learned in your previous classes. Okay, Snell's law, mu1. Sometime the refractive index is denoted by n. Okay, denoted by n. So n1 sin I is equal to n2 sin r. You may see in some books. Okay, now see here we'll be defining what is called refractive index. What is refractive index? What is refractive index? What is refractive index? You know, it is defined as, say, I'll write first mathematically. Refractive index, here I am just defining, denoting refractive index with mu. This is defined as the speed of light in the vacuum divided by the speed of light in the medium. Okay, I'll write refractive index. It is the ratio. It is the ratio of light. Ratio of speed of the speed of light, in vacuum to the speed of light in the medium. Okay, so refractive index of a medium is defined as the ratio of the speed of light in vacuum to the speed of light in that particular medium. Okay, as you see, this is the mathematical expression. This is the speed of light in the vacuum. So c is actually 3 into 10 to the power 8 meter per second approximately. Okay, and vm actually is the speed of light in the medium. Okay, we'll see what is called relative refractive index. What is relative refractive index? Suppose I have, as I was discussing, there are medium 1 and medium 2. Okay, medium 1 and medium 2. Refractive indices are like, say, mu1 and mu2. When I take relative refractive index of the medium 2, if I write relative refractive index index of the medium 2 with respect to medium 1, then how do we write this? This will be written as mu2 1. Okay, in some book it will be written like 1 mu 2, like that also. So this is say in this case I'll just tell you, see, when it is written mu2 mu 1, this means the refractive index of the medium 2 with respect to medium 1. And how do we write in terms of ratio? This will be written, see that the first index will go to the numerator and the second one go to the denominator. So mu2 by mu1. This is actually called relative refractive index. See, I'll just show you some good relationship. Okay, now we'll see, this is relative refractive index of medium 2 with respect to medium 1. That is mu2 1 is equal to mu2 by mu1. So in terms of speed, suppose within the medium 1 speed is v1 and the speed of light in the medium 2 is v2. In that case, you know, this I can write c by v2, this I can write as c by v1 in terms of the definition of refractive index. Okay, then you look here, this is mu1 by mu2. Okay, what is this? This is actually, see, refractive index is inversely proportional to the speed of light in that particular medium. Okay, see, a medium which has greater refractive index, suppose medium 1 has greater refractive index than medium 2, then this is one point. If mu1 is greater than mu2, then medium 1 is said to be optically denser, or we'll write denser, optically denser than the medium 2. Okay, medium 2. If refractive index mu1 is less than mu2 or mu2 is greater than mu1, then the medium 2 is said to be denser. Okay, optically denser medium. See, if I have, suppose this is medium 1, this is medium 2, and this has mu1, this has refractive index mu2, and if mu1 is greater than mu2, then this is denser medium, and this is rarer. Okay, rarer medium. Okay, denser medium and rare medium, like this. Okay, so these are relative refractive indices, and you can see this the speed of light in a medium where the refractive index is more. So the speed of the light will be less in that particular medium where the refractive index is more. Okay. See what are the consequences we can get from there. You look, suppose a ray is coming with a particular speed. Suppose this is denser medium. That means this is suppose mu1 and this is a rare medium. Rare medium where refractive index is mu2, and see here mu1 is greater than mu2. Okay, so this is the case here. So if that is the case, look what will happen. See, if that is the case, then the speed of light in the first medium is less. Suppose the speed of light is v1, here v2. So you know here what is happening, v1 is less than v2. So after refraction, light will be having greater speed. After refraction, that means in this medium, in the denser medium, the speed of light is less than the speed of light in the rarer medium. So that's why when a light refracts from denser medium to rare medium, then it actually goes away from, so this is the direction of the incident ray, so it will actually bend away from the normal. Okay, so it goes away from the normal when the light refracts from denser medium to rarer medium. Okay, I'll just take an example. So what I have written, see mu2 1 means mu2 by mu1. In terms of speed, it will be v1 by v2. v1 by v2. v1 by v2. Now, what we have learned, if suppose a ray is refracted from denser medium to rare medium, I'm sorry. Okay, let it go like this. So it will be difficult. Okay, still not good. I'll try to. Okay, so let this be here. So this is the interface. So if this is the denser medium and this is rarer. Suppose this is water, this is air. Air has refractive index 1, right? Mu2. Suppose this is mu2 has here mu a here 1, and mu w it has refractive index 1.33. So mu w is greater than mu a. So in this case, you know, the ray will be actually going away from the normal. This is the case, so it will go like this. Okay, see, the angle of refraction is greater than the angle of incidence, so this is greater than this. Okay, now see, this is mu to mu1. As I said, mu is actually inversely proportional to the speed of light in a particular medium. Okay, so now if we do the reverse, suppose a ray of light goes from air to water or refracts from air to water. So this is air and going to water. That means what? Here mu a is actually greater than mu. So mu a is greater than mu w. That means it is going from rare medium to denser medium. So refractive index is mu a is equal to 1 and mu w is equal to 1.33. That means speed of the light in the medium air will be greater than the speed of the light in the medium water. So that's why it will actually get bent toward the normal, like this. Get bent toward the normal. You look here, this is the I, angle of incidence, this is angle of refraction. So here angle of refraction is less than angle of incidence. Okay, so these are two things. So in very simple language, when a ray is getting refracted from denser medium to rarer medium, the refracted ray will be going away from the normal. But if a ray is refracted from a rare medium to denser medium, then the refracted ray will go towards the normal. Okay, towards the normal. So angle of refraction will be smaller than angle of incidence in case of refraction from rare to denser medium. Okay, now see, we should not confuse with the, okay, so let me first discuss about this particular comments. We should not be confused with the mass density and mass density with the optical density. So there are two terms actually now: optical density and mass density. What is optical density and what is mass density? So these two are not same. You might be thinking, we have learnt optically rarer and denser medium. Suppose, okay, so optically denser and rarer medium. See, optical density is actually, sorry, mass density is mass per unit volume, but optical density is nothing like that. If the refractive index is greater, then that is called denser medium optically. So how do you measure? Here you do the measurement with this, and here you do this mass density with actually rho. How much rho is there, or how much mass per unit volume is there in a certain material. So it is seen sometimes that rarer medium can have greater mass density, like turpentine. Okay, turpentine refractive index is less than turpentine. It has actually less mass density. Okay, is less than water. Okay, but optical density of water is less than the turpentine. Okay, see, water. So mass density is actually greater. So optically this turpentine is actually denser. So turpentine has greater optical density than the mass density. Okay, that means turpentine is a denser medium, while as the mass density of water is greater than the turpentine. Okay, so we should not get confused with the mass density and optical density. Optical density is measured by the refractive index. Okay, if the refractive index is greater, then that is denser medium compared to the other. But in case of mass density, if mass per unit volume is greater, then that is called mass density. All right, so let us look what is there here. So what is the cause of refraction then? What is cause of refraction of light? We have learned refraction means bending of light, and how it happens. because different media has got different refractive index, and the speed of light in different medium is different. That is the original cause. Light travels with different speed in different media. That is the reason why the light actually get bent or gets refracted, okay, with speed changing. Okay, there is a change in the speed. That is what we can say. That's why the bending of light happens. So cause of refraction is difference in the speed of light in different media, and that is actually caused by refractive index. Okay, so now we'll see some phenomena of refraction of light. Due to refraction of light, there will be a lateral shift of the image, or lateral shift of the refracted ray due to the refraction. Let us see what is called lateral shift. You can see there is a glass slab. So this is actually a glass slab. Glass slab. Slab means it has certain thickness. Okay. Sorry. It has certain thickness. So let us say that thickness is T or D, whatever T, let us say. Okay. And see, there will be two, like if something has to be viewed which is just below the slab of this glass, we certainly we do sometime. Okay, we just look through the slab of glass slab and see things just at the bottom of this slab. So in that case, you know, the ray of light actually, see, this is the incident ray. This incident ray is actually going like this, and then it get bent like this, and then it is emerging like this. Okay, this is actually emergent light. Okay, so this incident ray and emergent ray, they will be actually parallel to each other, but they see the path of, as you have seen already, that refraction, due to refraction, there will be bending of light. So there is a change in the path, but there is they are actually parallel to each other. See the angle of incidence, sorry, angle of incidence is I1 here, angle of emergence is R2. So since they are parallel to each other, it is seen actually this is I1 is equal to R2. And one more thing is, these two also will be equal to each other because they are in the same medium. Okay, all right. So this I1 and R2 are equal. What does this say? This say that the incident ray and the emergent ray, they are parallel to each other. So lateral shift means what? Now we'll see what is lateral shift. This was the original direction of incidence. This is after refraction. So the difference between these two, perpendicular difference or distance between these two rays, are called lateral shift. This is called lateral shift, and you look, lateral shift is the perpendicular distance between incident and emergent rays when the light are incident obliquely on a refracting slab with parallel faces. Okay, now see what will be this. See, this is actually lateral shift. Lateral shift. Okay, this is lateral shift. But what will be the normal shift or shift, perpendicular shift or vertical shift? Will show you here. There will be vertical shift also. Not only lateral shift, there will be vertical shift also, and I will see how it is. Then we will go to the internal reflection. Okay, so we'll just go to the next phenomenon. This is actually normal shift. We often see this. This happens to us also. Suppose you are uh, you are given a container of water, and a 5 rupee coin is just placed at the bottom of the container. I'm sure that you will not be able to pick that coin at single chance, because see, originally the coin may be here, but due to refraction, see, light gets bent so much that we will see this coin at here O prime. So this is a container of water, and this is the bottom part of the container. See, sometimes it is seen that the bottom part is actually raised up to here. That's why you sometimes may think that a pond or any pool may have less depth, but that is actually apparent depth we are seeing. See, what is this? Look, I'll tell you. So this quantitatively, this normal shift, because so this is seen when we see normally, okay, or near to the normal, then we see this defect, okay, generally. So this effect is called normal or vertical shift. I think I should write it normal shift. Normal shift, okay. And this normal shift actually, see, there are two terms. One is called real depth, another one is called apparent depth. See, after refraction of light, see, as I showed or as I said, the 5 rupee coin will be seen here. Actual depth is the total height, okay, total depth, okay. This is the depth, this is h2, this is actual depth, okay. I'm sorry, this is h1 is actual depth, okay. h1 is actual depth, suppose 10 centimeter, okay. h1 is 10 centimeter, and h2 is actually the apparent depth. H2 is apparent depth. What is apparent depth? I think H2 is real depth, and apparent depth is H1 here according to the figure. See the depth, this one is actually apparent depth, okay. So normal shift is actually equal to real depth, like it is the difference between the real depth and apparent depth, H2 minus H1, okay. H2 minus H1, and mathematically what will be the shift? See, refractive index is equal to real depth divided by apparent depth. Okay, this is actually refractive index of the medium, okay. Suppose in this case water it is, okay. So the normal shift is, So this is actually, this is apparent. See, we can find out the apparent depth from this particular position, this particular equation. Okay, then we can put it here to get the normal shift. Okay, this is actually normal shift numerically, normal shift. Okay, so real depth is h1, in this case h2, sorry, real depth is h2 minus h1 in this figure, according to this figure. Okay, this is normal shift. All right, I think I'll stop it here for today. There was some issues in between, software issue. I'll continue this class in the next session with the TIR and other effects, natural effects due to TIR, total internet reflection. Okay, so thank you for your patience. Bye for today.